March 1944. R.A.F. Debden, England. A P-47 Thunderbolt fuel tank sits on the maintenance bench. External drop tank, 108-gallon capacity. Aluminum construction with internal baffles. It should be scrap. 3 bullet holes pierce the lower quadrant. Clean entry wounds from 7.92mm rounds. Luftwaffe standard issue. The tank returned half full after an escort mission to Brunswick. No fire, no catastrophic failure, no fuel streaming into the slipstream at 25,000 feet. Tech Sergeant William Marsh turns the tank slowly under the work light. The punctures show dark staining around the edges where rubber compounds swelled on contact with fuel, sealing the breach. Inside, the self-sealing layers did exactly what they were designed to do. Stamped on the manufacturing plate, Inspector 2847K, a woman's shift code from a factory in Evansville, Indiana. The Luftwaffe had calculated P-47 range down to the minute. They knew when the escorts would turn back. They planned for it. They never planned for Thunderbolts that refused to leave. Someone far from the front made sure of that. Her name might have been Dorothy, or Helen, or Margaret. The records call her Inspector 2847K. Third shift, vulcanization specialist, Republic Aviation Subcontractor Facility, Evansville, Indiana. She arrived at the factory floor at 2300 hours, 6 nights a week, punched her time card, changed into work coveralls, tied her hair back under a regulation headscarf. The factory floor stretched 300 feet under overhead lighting that turned night into permanent fluorescent day. She worked alongside machinists who formed aluminum sheets into cylindrical tanks on pneumatic presses. Besides seamstresses who stitched fabric layers that would become the outer skin of self-sealing systems. Beside press operators who laminated rubber compound between those fabric layers under controlled temperature and pressure. Beside gaugers who measured seam tolerances in thousandths of an inch with calipers that clicked softly in the industrial noise. They built fuel tanks for the P-47 Thunderbolt, not the glamorous work, not the airframe with its distinctive razorback fuselage, not the Pratt & Whitney R2800 engine producing 2,000 horsepower, not the 8.50 caliber machine guns, the plumbing, the unglamorous essential plumbing that held aviation fuel and kept pilots alive. The P-47 carried 305 gallons internally. Main fuselage tank held 205 gallons positioned behind the cockpit. 2 wing tanks held 50 gallons each, positioned in the wing roots near the fuselage junction. The internal capacity provided approximately 2 hours of combat flight at normal cruise settings. Enough for local defense. Enough for short-range interception. Not enough for deep escort missions into Germany. The tactical problem was mathematical and unforgiving. Early P-47 missions in late 1943 escorted bomber formations to the German border and turned back, fuel exhausted. The bombers continued alone into the heart of the Reich, into the guns, into the fighters. Losses climbed. September 1943. 8th Air Force bombers struck Stuttgart without fighter escort for the final leg. Luftwaffe fighters swarmed the formations. 45 bombers failed to return. 450 men gone. October 1943. The second Schweinfurt raid penetrated deep into Germany, targeting ball-bearing factories. 60 bombers lost. 600 casualties. The crews called it Black Thursday. The mathematics were simple and terrible. Unescorted bombers died at rates that no Air Force could sustain. Bomber Command needed fighter protection over the target, not near the target, not approaching the target, over the target and all the way home. That meant P-47s needed more range, more fuel, more time over Germany, before the gauges forced them to turn for home. The distance from English bases to Berlin measured 600 miles. Round trip, 1,200 miles. Add combat maneuvering, add reserve for emergencies, add contingency for weather. The mission profile demanded fuel capacity that the P-47's internal tanks could not provide. External drop tanks offered the solution. Belly-mounted tanks carrying 75, 108 or 150 gallons depending on mission requirements. The pilot burned external fuel first during transit. Over the target area, he jettisoned the empty tanks and fought on internal fuel, the disposable range extension that made deep escort possible. But external tanks were only useful if they worked, if they fed fuel reliably, if they sealed properly at altitude where low pressure and cold temperatures tested every joint and gasket, if they survived the minor damage that combat operations made inevitable, and most critically, if they incorporated self-sealing technology that prevented catastrophic fuel loss when enemy fire found them. Self-sealing fuel tanks were not negotiable by 1943. American doctrine had learned the lesson that Japanese designers ignored. Unprotected fuel tanks killed crews. Protected tanks brought them home. The technology was sophisticated and demanding, multiple layers working together. Outer fabric for structure, vulcanized rubber for the primary seal, inner gum rubber layer that swelled on contact with fuel when punctured. The swelling closed the hole, the seal held, the fuel stayed contained. The layers had to bond perfectly, no delamination, no air pockets, no weak points where seams met. The rubber compound had to cure at precise temperatures for exact durations. Too hot and the rubber degraded. Too cold and it failed to bond. The timing mattered. The temperature mattered. Everything mattered. Inspector 2847K checked the work. She ran her gauges across seam welds. She monitored curing temperature in the vulcanization chambers. She tested samples in the water bath pressure system, watching for bubbles that revealed leaks invisible to the eye. She signed her inspector code on tanks that met specifications. She rejected tanks that failed. Her signature meant the tank would seal under pressure at 25,000 feet. It meant the tank would feed fuel reliably through transfer lines to the engine. It meant the tank would survive minor combat damage and keep its pilot alive long enough to reach home. Her work connected directly to survival. Every tank that left the factory floor would hang beneath a P-47 over Germany. Every seal she approved would face Luftwaffe guns. Every signature carried the weight of men she would never meet flying missions she would never see. Range is math. Math is survival. And survival began in Evansville with workers who understood that their precision determined whether bomber crews came home. The fuel system was not an accessory. It was not an enhancement or an upgrade or a nice-to-have modification. It was the difference between a fighter escort that protected bomber crews and a fighter escort that abandoned them 200 miles short of the target. The difference between returning crews and empty bunks. Colonel Hubert Zemke commanded the 56th Fighter Group flying P-47's from Halesworth, England. He understood the mathematics with brutal clarity. His fighters could escort bombers to the German border on internal fuel, perhaps 20 miles beyond if pilots pushed the mixture lean and prayed the headwinds stayed light. Then the fuel gauges demanded a choice. Turn back or die over Germany with empty tanks. The bombers continued alone, and the Luftwaffe waited. German fighter tactics evolved specifically to exploit the escort gap. Luftwaffe controllers tracked American formations with radar and ground observers. They calculated the moment when P-47's would reach their fuel limits and turn for home. They waited. Then they struck. The attacks came in waves. Focke-Wulf 190S dove from high altitude with cannon and machine guns converging on bomber formations that had lost their protective screen. Messerschmitt 109s followed, targeting damaged aircraft that fell behind the formation. The bomber gunners fought back, but defensive fire could not replace fighter protection. More missions, and deeper targets, and not enough fuel. January 1944. 8th Air Force planners identified targets in central Germany that strategic bombing doctrine demanded attacking. Aircraft factories, ball-bearing plants, synthetic fuel refineries, all beyond P-47 range on internal fuel alone. The external drop tank program accelerated from experimental to essential. Republic Aviation's engineering team designed tanks that could mount to standard P-47 hardpoints without airframe modification. Subcontractors across the Midwest received specifications for production, but early results revealed problems that specification sheets could not predict. February 1944. P-47's departed English bases carrying 75-gallon drop tanks for a mission to Frankfurt. At 20,000 feet, pilots reported fuel transfer failures. The tanks pressurized improperly in the thin air. Feed lines froze. Valves failed. Fighters jettisoned useless tanks and turned back short of the target area. The bombers they were supposed to protect continued without escort. 21 bombers failed to return. March 1944. Improved 108-gallon tanks entered service with modified pressurization systems. The capacity extended range significantly. Pilots could reach targets deeper in Germany. But combat revealed a new problem. Luftwaffe fighters began targeting the external tanks deliberately. A few rounds through the thin aluminum skin meant catastrophic fuel loss. Fighters that took hits to drop tanks lost their range extension immediately. Streaming fuel behind them, they jettisoned the damaged tanks and faced the same choice. Turn back or run dry over hostile territory. 3 P-47s went down in a single mission, not from combat damage to vital systems, from fuel starvation after drop tanks were hit and pilots miscalculated their remaining range to friendly bases. The engineering problem was clear. Drop tanks needed the same self-sealing technology that protected internal fuel systems. But applying that technology to disposable external tanks created complications that standard internal tanks did not face. External tanks operated in extreme conditions. Temperature swings from ground-level warmth to minus 40 degrees Fahrenheit at altitude. Pressure changes from sea level to 25,000 feet. Vibration from engine harmonics and airflow, all while hanging from external hardpoints that subjected the tanks to forces internal systems never experienced. The self-sealing layers had to function across that entire operating envelope. The rubber compound had to remain flexible at altitude cold. The fabric layers had to maintain integrity under pressure differentials. The seams had to seal perfectly despite vibration and thermal expansion. And the tanks still had to be disposable, inexpensive enough to jettison over Germany, light enough not to penalize aircraft performance, simple enough to manufacture in the thousands needed for sustained operations. The specifications demanded perfection at scale, self-sealing technology that worked reliably, manufacturing precision that delivered consistency across thousands of units, quality control that caught failures before tanks reached operational squadrons. March 1944. 8th Air Force flew 24 missions deep into Germany. Fighter escorts turned back on 18 missions due to fuel limits. Bomber losses on unescorted portions of missions exceeded 8% per raid. The casualty mathematics were unsustainable. If the airplane must go farther, the tank must hold. Not most of the time, not usually, not on average. Every time, every tank, every mission. The weakest point becomes the most tested part. Combat finds failures that factory inspections miss. Altitude reveals seal problems that ground tests don't detect. Enemy fire exploits any weakness in construction or materials. The factories built tanks by the thousands. The inspectors checked them by the thousands. And over Germany, pilots staked their lives on work done by women they would never meet in factories they would never see. The pressure fell on the production line, on the machinists and the vulcanization specialists and the inspectors who signed off on work that would face Luftwaffe guns at 25,000 feet. The solution existed. Self-sealing fuel tank technology had protected Allied aircraft since 1940. British engineers developed the core principles. American manufacturers refined them for mass production. By 1944, the chemistry and construction methods were well understood. Applying that knowledge to external drop tanks required precision at every step. The process began with raw materials, natural rubber compound mixed with additives that controlled swelling rates and curing temperatures. Fabric reinforcement woven tight enough to provide structure but flexible enough to conform to tank contours. Aluminum sheet metal formed into cylindrical shapes with rolled seams and welded joints. Each component arrived at the factory floor with specifications measured in thousandths of an inch. Each would be assembled in sequence by workers who understood that gaps or bubbles or weak bonds meant failure over Germany. The outer layer was fabric, cotton or synthetic weave treated with fire-retardant compound. The fabric provided structural integrity and protected inner layers from abrasion and environmental damage. Seamstresses cut patterns precisely. The material was stretched over, forming dies without wrinkles or folds that would create weak points. The middle layer was vulcanized rubber, black compound that cured hard under heat and pressure. This layer formed the primary fuel barrier. It had to be thick enough to seal effectively, but thin enough not to add excessive weight. The rubber arrived in sheets that workers cut and fitted to exact dimensions. The inner layer was gum rubber, softer compound that remained tacky and elastic. This was the critical sealing element. When punctured and exposed to fuel, the gum rubber absorbed hydrocarbons and swelled. The swelling closed holes. The seal held. Chemistry became armor. Inspector 2847. Kay watched the lamination process with eyes trained to catch imperfections. Workers placed fabric, then vulcanized rubber, then gum rubber in sequence on the forming die. The layers went into steam-heated presses that applied precise pressure at controlled temperature. The temperature had to reach 280 degrees Fahrenheit, not 270, not 290. The chemistry demanded exactness. Too cool, and the rubber failed to cure properly. Bonds between layers remained weak. Too hot and the compounds degraded. Molecular structure changed. Sealing properties failed. The pressure had to be maintained evenly across the entire surface. 50 pounds per square inch distributed uniformly. Uneven pressure created voids where layers failed to bond. Air pockets that would expand at altitude and separate the laminate. Curing time was calculated in minutes. The presses held for exactly 12 minutes at temperature. Workers monitored gauges. Steam hissed through heating channels. The smell of hot rubber filled the factory floor. When the press opened, the laminated material emerged as a single bonded unit. 3 layers now functioned as one. The assembly moved to the next station where workers fitted it into the aluminum tank shell. The seams were critical. Where laminate edges met, where fabric overlapped, where the seal had to remain continuous without gaps. Workers applied adhesive compound to seam areas. They pressed the edges together with hand rollers. They checked alignment with straight edges and squares. Chalk lines marked where seams should fall. White marks on black rubber that showed any deviation from specifications. the lines had to align within 1/16 of an inch. Larger variations meant rejection. The assembled tanks moved to the testing station. Water bath pressure tests revealed what eyes could not see. Tanks were submerged in clear water tanks. Air pressure was applied to the interior, 15 pounds per square inch, higher than operational requirements, but the test needed to stress the seals beyond normal limits. Bubbles meant failure. Tiny streams of air rising from seams or penetrations or weak spots in the laminate. Workers watched the water surface. Sometimes the leak was obvious, a steady stream of bubbles from a poorly sealed seam. Sometimes it was subtle, a single bubble emerging every few seconds from a pinhole in the rubber. Any leak meant rejection. The tank was pulled from production. Workers examined the failure point. They determined whether the problem was material or process or human error. They made corrections. The tank was scrapped or rebuilt. Tanks that passed water testing moved to fitting installation. Fuel transfer valves threaded into mounting bosses. Go-no-go gauges checked thread engagement. The fittings had to seal perfectly. A dripping valve at altitude meant fuel loss. Fuel loss meant reduced range. Reduced range meant turning back. Calipers clicked as workers measured fitting depths. The threads had to engage fully without bottoming out. Too shallow and vibration could loosen the connection. Too deep, and the fitting could crack the tank boss. Not pretty, but airtight. The final inspection station was where Inspector 2847K applied her stamp. She checked the test documentation. She examined the seams visually under bright light. She verified that fitting torque values met specifications. She confirmed that the manufacturing lot numbers matched the material certifications. Then she stamped her code on the data plate. Inspector 2847K. The mark that meant this tank met every specification. The signature that said this tank would work at altitude. The guarantee that this tank would seal when hit and keep a pilot alive long enough to reach home. The weakest point becomes the most tested part, and the factories made certain that the weakest point could survive. April 1944. The tanks arrived in England by convoy. Wooden crates stacked in cargo holds, marked with specifications and lot numbers. 108-gallon capacity. Self-sealing construction. Inspector codes stamped on data plates from factories across Indiana, Ohio, Pennsylvania. Ground crews uncrated them at bases across East Anglia. They mounted them to P-47 hardpoints using standardized attachment hardware. They connected fuel transfer lines to aircraft systems. They ran pressure checks to verify seal integrity after shipping and handling. The tanks hung beneath Thunderbolt bellies in neat rows. Aluminum cylinders that extended range from 475 miles to 800 miles. The difference between turning back at the German border and staying with the bombers all the way to the target. The missions pushed deeper. Brunswick, Kassel, Leipzig, Berlin. May 1944. The 8th Air Force flew coordinated strikes against aircraft factories and fuel infrastructure deep in central Germany. P-47 groups provided escort from departure to target and back to English airspace. The Luftwaffe rose to intercept expecting fighters to break off at the usual points. They stayed. The escorts that were supposed to turn back at the border kept coming. P-47 set, that should have been at fuel limits, still had time over the target. Thunderbolts that German controllers calculated would be gone remained on station. Luftwaffe, tactical doctrine had not prepared for this. German fighter tactics depended on the escort gap. Wait for the Americans to leave, then strike the bombers. The doctrine worked when P-47s flew on internal fuel alone. It failed when the escorts refused to leave. Combat reports from German pilots began noting the change. American fighters now escort to target areas previously beyond their range. Thunderbolts remain over target zones where fuel should force their withdrawal. The confusion was tactical and strategic. If American fighters could reach any target in Germany, nowhere was safe. The external tanks made it possible, but the self-sealing technology made it sustainable. June 1944. Lieutenant Robert Johnson of the 56th Fighter Group escorted bombers to a target near Munich. His flight encountered Focke-Wulf 190s at 24,000 feet. The engagement was brief and violent. Johnson's P-47 took hits. Cannon shells struck the drop tank. The tank did not explode. The fuel did not stream away. The self-sealing layers absorbed fuel and swelled. The punctures closed. Johnson continued the mission on partial drop tank fuel, plus his internal supply. He jettisoned the damaged tank over the target and flew home on internal fuel. He landed at Halesworth with fuel to spare. Ground crews examined the jettisoned drop tank recovered from another P-47 that landed early. 3 entry holes. Dark staining where rubber compound sealed around the punctures. The tank had held perhaps 40 gallons when hit. It retained most of that fuel until jettison. Without self-sealing construction, the same hits would have meant immediate fuel loss. Johnson would have faced the choice of turning back immediately or continuing and risking fuel starvation. The sealed tank gave him options. Options meant survival. They covered. They came home. July 1944. The pattern repeated across hundreds of missions. P-47’s took hits to external tanks and continued operations. Pilots jettisoned damaged tanks that had retained enough fuel to extend their range into Germany. The tanks were disposable, but they did not fail catastrophically. They leaked rather than exploded. They held rather than streamed. The statistics told the story. Bomber losses on escorted missions dropped to 3% per raid. Losses on unescorted portions of raids had exceeded 8%. The difference was measured in crews that returned rather than empty bunks and memorial services. August 1944. A damaged drop tank returned to Debden among the aircraft maintenance salvage. Tech Sergeant Marsh pulled it from the pile and set it on the bench. The tank had done its job. It had extended a P-47's range deep into Germany. It had taken hits and sealed. It had kept a pilot in the fight long enough to matter. The inspection plate showed the stamp. Inspector 2847K, a code from a factory in Indiana. A woman whose name the records did not preserve, but whose work travelled 4,000 miles to face combat over Germany. The Luftwaffe fought pilots. They trained to engage enemy aircraft in aerial combat. They developed tactics to exploit American fighter limitations. They calculated fuel ranges and escort radii and planned their attacks accordingly. They should have feared the factories, the workers who built systems that extended range beyond German calculations, the inspectors who caught failures before tanks reached combat, the machinists and vulcanizers and seamstresses who made the self-sealing technology work at scale. Strategic advantage was built in Evansville and shipped in crates. It hung beneath P-47's as unglamorous cylindrical aluminum tanks. It sealed when hit because workers on third shift made certain the rubber compound cured at exactly 280 degrees for exactly 12 minutes. The bullet scars showed where Luftwaffe rounds punched through aluminum skin. The dark staining showed where gum rubber swelled and sealed. The tank held. The pilot survived. The mission continued. Combat validated what the factories promised. Precision at scale became a weapon. Quality became survival. The numbers tell part of the story. By September 1944, 8th Air Force P-47's flew escort missions to every major target in Germany. Range limitations that had defined operations in 1943 no longer dictated tactical planning. The external drop tank system worked, reliably, consistently, at scale. Bomber losses on fully escorted missions stabilized at sustainable rates. Crews completed tour requirements and rotated home rather than disappearing over Germany on their 8th or 12th mission. The attrition curve that had threatened to break 8th Air Force bomber operations flattened because fighter escorts stayed with the formations. But the numbers only capture outcomes. They do not explain how those outcomes became possible. The engineering was sophisticated but not revolutionary. Self-sealing fuel tank technology existed before the war began. The chemistry of rubber compounds that swelled on contact with hydrocarbons was understood. The construction methods for laminated fuel cells were established. What changed was the application of that technology to disposable external tanks manufactured in quantities sufficient to supply sustained deep penetration missions. That required industrial capacity, quality control systems, workers trained to recognize when seams did not align or when curing temperatures drifted outside specifications. It required women like Inspector 2847K who understood that their signatures meant something beyond factory paperwork. The stamp on a data plate connected directly to a pilot at 25,000 feet over Germany, making calculations about fuel remaining and distance to target, and whether he could stay with the bombers or had to turn back. The connection was invisible, but absolute. The work done in Evansville determined what was possible over Berlin. The precision achieved on third shift in an Indiana factory defined the tactical options available to fighter groups operating from English bases 4,000 miles away. American industrial strategy in World War II depended on this principle. Quality at scale. Not one perfect prototype, but thousands of reliable production units. Not experimental technology, but proven systems manufactured consistently across multiple facilities by workers who had never built aircraft components before the war. The Liberty Women represented a workforce transformation that occurred across American industry between 1942 and 1945. Women moved into manufacturing roles that had been exclusively male before the war. They operated machine tools and welding equipment and precision measurement instruments. They learned trades in weeks that had traditionally required years of apprenticeship. They made it work because failure was not abstract. Failure meant aircraft that did not return, pilots who did not come home, bomber crews lost because fuel tanks leaked, or seals failed, or fittings did not hold pressure at altitude. Inspector 2847K did not know the pilots who flew with her tanks. She never saw the aircraft they protected. She worked third shift in an Indiana factory, while those pilots slept in England preparing for morning missions. The war connected them without ever bringing them into contact. Her contribution was measured in what did not happen. Tanks that did not fail. Fuel that did not stream away when hit. Pilots who did not face impossible choices about turning back or pressing on with insufficient fuel. More time, more reach, more survivors. The external drop tank program enabled the strategic bombing campaign that planners had envisioned but could not execute in 1943. Fighters escorted bombers to any target in Germany. The Luftwaffe could no longer wait for the Americans to leave and then strike undefended formations. Air superiority shifted decisively because American fighters had the range to maintain presence over German airspace. That range came from tanks built by workers whose names the historical record largely forgot. Production statistics survive. Manufacturing specifications exist in technical archives. But the individual workers who achieved quality at scale remained mostly anonymous. Inspector 2847K is a composite representing thousands of women who performed similar work at facilities across the United States. The specific inspector code comes from salvaged tanks examined after combat. The details of her work reflect documented manufacturing processes for self-sealing fuel systems. But her individual identity is lost. What remains is the work itself. The tanks that hung beneath P-47 Thunderbolts and extended their range into Germany. The self-sealing systems that survived combat damage and kept pilots alive. The quality control that made disposable tanks reliable enough to stake missions on. The forewoman stamp fades with use. Metal wears, data plates corrode. The tanks themselves were designed to be jettisoned and lost. Few survived the war in any condition that preserved inspector markings. But the range those tanks built does not fade. The strategic advantage they provided shaped the outcome of the air war over Europe. The lives they saved do not appear in production statistics, but they represent the ultimate measure of the work's value. Craft over credit. The unglamorous precision of factory work translated into tactical advantage over Germany. The hands behind the range rings changed the air war, not through innovation or invention, but through mastery of existing technology applied at scale with consistency that combat operations could depend on. The Liberty women built the fuel systems that stunned the Luftwaffe. They did it one tank at a time, one inspection at a time, one signature that guaranteed the work met specifications and would function when tested by altitude and combat, and the desperate calculations of pilots trying to bring their crews home.